Alright, this video is going to be about buck converters, and I'm going to start with some working principles from which we can derive certain characteristics like the transfer function of the buck converter, and with that we can further calculate what sort of inductances and what sort of capacitances we need for an actual design. So first I'm going to start off by defining some of these components. So this is the basic structure of the buck converter, and I'm going to start off by defining this as VL and this as V out, and this is V in. Do the same for the off state. So if we just look at this circuit, we can see that when this switch, typically a MOSFET, so when this switch is closed, the voltage across this inductor is going to be V in minus V out. And then when the switch is open, we can see that this diode is on. So this is basically all one node, and this is all one node. So then the voltage across the inductor is going to be negative V out, which I mislabeled here, V out. So if we just draw a random switching cycle for this buck converter, so we can say this is just arbitrary. So this is when the switch is on, and then this is when the switch is off. So I'm gonna make some plots here. If I could draw well, that's fine. So the whole purpose of this buck converter really is to convert this input voltage to a lower output voltage, right? So the way we do that is by turning on and off this switch, and the transfer function for this, which is basically going to tell us, so we put this voltage in, then this is our buck, so we get this voltage out, right? So this is going to be, this thing is going to have a transfer function that will be some sort of equation where V in is equal to something times V out, basically. So that's what I'm going to explain first. How do we solve that? So the switch is turning on and off, and this is going to be labeled as T on, and then this is going to be T off. That doesn't look like off. T off. And then the total time is going to be capital T, the period, where the period is the inverse of this frequency. And then we're also going to define that T on is equal to the duty times total period. So then T off is equal to 1 minus the duty times the period. So the duty is always going to be greater than 0, or greater than or equal to 0 and greater than or equal to 1. So when the duty is 0, it's always off, and when the duty is 1, it's always on. So when the duty is 0.5, it's on for half the period and then off for the other half of the period. And so if the duty is 0.25, it's going to be on for 25% of the period and then off for 75% of the period, right? So based on this switching, if we look at the circuit when the switch is on, so the switch is closed, we'll see that the voltage across the inductor, like I said earlier, is V in minus V out. So that's going to be a positive voltage. So this is V in minus V out. And then when the switch opens, the voltage across the inductor is going to be negative V out. So then turns back on, turns back off. So this is negative V out. So based on that, we can do some calculations of the transfer function now, based on the volt-second balance. So from the volt-second balance, we're basically saying that the voltage across this inductor is going to be an average value of 0 as it's switching in steady state. So if the average value across one period is going to be 0, so for one period, let me zoom in more. So for one period, the voltage across the inductor with respect to time is going to be equal to 0, right? Maybe I can write a little smaller. So from this, we can assume, so the voltage over one period divided by the total period is going to be the average voltage of the period, right? That's what this is saying. So then if we just do some algebra, this is just going to cancel out, right? Just multiply both sides by t. So, and then we can separate the on time from the off time. So we can write from 0 to t on, the on voltage with respect to time plus the integral from t on to the full period. This is for the off time. Is equal to 0. So having that written out, we can then see that this area is actually going to be this area right here, right? And then this area is going to be this negative area right here. So this area is actually going to be V in minus V out, right? It's a square or a rectangle. V in minus V out times the on time. And then this is going to be negative V out times the off time. So you can rewrite this as VL on times on time plus VL off times off time. And that equals 0. So then if we keep doing some algebra, we can see that VL on, remember, is V in minus V out. This is V out average times T on plus negative V out times T off. So then from that, we can calculate that. So T on, remember, and T off are equal to D times T, and T off is equal to 1 minus D times T, capital T. So if we plug those in here, so and 1 minus then we ultimately get this. The output voltage is going to be equal to the duty times the input voltage. And this is going to be in continuous conduction mode. So basically continuous conduction mode is going to be when the output current is always positive value. So in continuous conduction mode, the output current is going to look like this, right? This is I out T. This is T. And then we can, so this is continuous conduction. And then when the bottom is barely touching 0 amps, this is going to be boundary conduction. And then when it goes below, it's going to be like this. It's going to get chopped off at the bottom. That's going to be discontinuous conduction. So this is for continuous conduction. And boundary conduction is basically just a special case of continuous conduction. It's still continuous conduction, but it's about to be discontinuous. So now that we have this transfer function defined, this is an important one. This is basically the whole point of the converter, right? We have this device and we're trying to take a high voltage and we're trying to drop it to a lower voltage for whatever purpose is necessary, right? So now with this information, we can further investigate what the current in this inductor is going to be, which is important because the average current in this inductor is actually going to be the same as the output current to this load. This is the load right here. So we need to consider the equation for the relationship between voltage and current in an inductor. So the voltage of an inductor is going to be equal to the inductance times the rate of change of the current with respect to time. So basically, if we have this, we have the plot of the inductor voltage, we can assume the shape of the waveform for the inductor current. So this is a constant voltage, V in minus V out, a constant positive voltage. So the slope of this is going to be a constant positive slope, right? The rate of change of the current is going to be equal to this constant voltage, proportional to. So then we can see that during the off period, the voltage is a negative value. So the inductor current is going to be a constant negative slope. So drop down to there. And then when it turns back on, it's going to rise back up and then drop back down. Right? So we will define this as IL min and this as IL max. And then the average value this is going to be IL average. This bars represents average, which is actually equal to I out average. This is equal to I out average because this capacitor here, if you think about it, basically acts as an open circuit for DC current, and depending on its value acts as a short circuit for AC current. So this AC current is actually getting synced by this capacitor basically, and then the DC current is getting passed to the load. So the average of this inductor, the average of this inductor current is equal to the average of the output. So with this information, if we zoom in on this, we'll basically see this is the waveform. I'll draw that a little better. This is the waveform we're getting. So let's draw some better lines. Use this. All right. Just drawing some lines to section this off. So this, as we discussed, is the on time, which is equal to D times T. And this is going to be the off time, which is equal to 1 minus D times T. And then this is IL max. And this is IL min, as is this IL min. Okay. So just draw this. Separate these sections. So now that we have that, and basically the output current is basically going to be determined by your load, right? So your load is going to just be drawing a certain amount of current, and depending on what load you're designing this for, you'll need to ensure that the inductors can handle this amount of current, which I'll go over after we discuss how we calculate this IL average and the delta IL. So this from here to here is going to be delta IL. So, and then this is IL average. Okay, so IL average is actually going to be the average value over this period t of these two trapezoids right here. This trapezoid and this trapezoid. So if we write that all out, it's going to be really long. So it's going to be IL is equal to 1/2 IL min plus IL max times dt plus 1/2 IL min plus IL max times 1 minus dt times t all over t, right? So basically I'm just going to shorten it and forget about the algebra and just tell you that IL average is actually equal to IL min plus IL max divided by 2. So it's basically just the average value of IL min and IL max. And then how do we get delta IL? So delta IL is equal to IL max minus IL min, right? But how do we solve that? So remember before I was talking about VL is equal to L di dt. So let's use the case for the on period. Solving this will be the same outcome regardless of if we solve this slope for the on period or the off period. So using the on period, we're going to get this. VL is equal to, so VL for the on period is equal to L times di for the on period over, well, L for the on period over change in time. So then from that we can calculate that di L on dt is equal to VL on, remember for the on period, is V in minus V out. So this is equal to V in minus V out divided by L. So then, if we want to know delta IL, over this period of time, right? This is, say this is 0, this is T on, right? So we know this slope, so we know this slope is going to be in amps. So it's going to be in amps per unit of time, so amps per second, right? And we know the amount of seconds that it takes to go from here to here, which is delta IL. We just multiply the amount of time it takes to go from IL min to IL max by this slope, and that gives us the total change in current. So delta IL is going to be equal to T on times DIL on, which we solve with this, times dt. And then this is also equal to T on, remember, is d times the period times DIL. Or we can simplify it even more. Just say V in minus V out over L is equal to delta IL. Nice. All right. So with that said, now we can calculate the critical inductance. So when we're calculating the critical inductance, we're going to want to choose the lowest percentage of the maximum load that we want to keep at continuous conduction, which is going to be barrier conduction. So critical inductance. That's awful handwriting, but I'm writing with a mouse, so let's see. So we're gonna have to have a current limit that we can output, right? Or your load is just gonna have a certain maximum that it can output. So we're either gonna be limited by the load, or we're gonna be limited by our converter. What is the maximum current we can output from this converter, you know? So that's gonna be I out max. And then for the critical inductance, we want to know I out min, which is going to be equal to some percentage x percentage times I out max. An example of this could be 10%. So with that, we're going to need to calculate what the inductor will need to be to maintain barrier conduction mode. So remember this plot, the output current is going to be going like this, right? So at barrier conduction, it's barely going to be touching the bottom, because this is going to be I out max. These are actually averages, so you need a bar above them. And then this is going to be I out min. This is I out. This is T. Okay, so how do we calculate what inductor will provide us with barrier conduction mode at some minimum output current? That's what we'll calculate now. So start from up here. So IL min is going to be equal to IL the, so this IL min is going to be the minimum of this plot. Remember, this is IL min. So IL min is equal to the average output minus the total change in current divided by 2. That makes sense because this distance is delta IL over 2, right? This whole distance from IL min to IL max is delta IL. So half of that distance is the distance from IL average, should be a capital, from IL average to IL min. Okay, so that's going to be equal to, as we said before, IL min let me just write it over here. IL min, as we said before, is equal to, or not IL min, IL average, as we said before, is equal to I out average. So we can rewrite this as I out min average times delta IL minus delta IL over 2. So we need to further substitute the equation we have for delta IL. So then we're going to get IL min is equal to I out minus all of this d times t times v in minus v out all over L, right? Yeah. And then this is all divided by 2. So then we can further simplify this by saying V in, remember from our transfer function, let me draw this arrow better. So V out is equal to the duty times V in. So V in is going to be equal to V out divided by the duty. So then we can rewrite this as IL min is equal to I out min minus d times t times V out over d minus V out over 2L. So remember t, the period, is the inverse of the frequency, right? So if we finally simplify, we can get the equation that IL min is equal to I out min average minus, so taking this V out out and then multiplying this D in, we get V out, these are V out average, so V out average times 1 minus D over 2. Remember, T is the inverse of frequency, so 2FL. And then recalling that we're calculating IL min, or we're calculating I out min average when the absolute minimum of the inductor is going to be at 0. So IL min here is going to be 0. So we're basically setting this whole equation equal to 0. And then we can rearrange that. Just doing some algebra. We get L is equal to V out L is equal to V out average times 1 minus D over 2F I out min. And that's how we select the capacitor, or the inductor, excuse me. This is important. That's going to be this inductor. So the next thing we're going to talk about is going to be the output capacitor. So the output capacitor from the circuit you can see is oriented like this. This is our load. So this is I out. IL and IC. So we're denoting the capital letters as a DC current and the lowercase letters as an AC current. So we know that IL is going to be like this, right? With respect to time. And then this current is going into this node and then branching at these two nodes. And by nature of the capacitor will block DC current and accept AC current to pass, right? Let's extend this a little bit. So then I out, the DC current is going to get blocked from going through the capacitor and go to the load. So I out is going to be this DC value, and then IC is going to be the AC component of this waveform. So this is I out. And then this is going to be IC. And then the way we're going to calculate the capacitor we need for this, the critical capacitance, is with this equation. The charge is going to be equal to the capacitance times the voltage ripple. So delta V is going to be between these two values, right? So the way we can calculate this with IC versus T is Q. This is actually going to be equal to, maybe I should draw this a little bit bigger. Let me redraw this. So right? The area under this is actually plus Q, and the area under this is actually minus Q. So then, just by solving the geometry, this is going to be equal to that area under the curve of current versus time. So then we can get delta IL over 8 times the frequency. It's equal to the output capacitor times delta V rearranging that, C out equal to delta IL over 8F, and then that is actually times delta V out. And then recalling our equations for delta IL, you get the final form C out equal to 1 minus D divided by delta V out over V out times 8 times L times F squared. Circle that in red. This equation is considering this this is what we refer to as the voltage ripple, or the output ripple. This is equal to voltage output ripple. So from this, you can see that if we wanted the output voltage ripple to be super small, this is basically the output voltage ripple is the proportion of the output voltage peak to peak value versus the average value. So the ratio of the output peak to peak divided by the average output voltage. And if ideally you want that to be 0, but when you're trying to minimize that, you can tell from the equation, as the voltage ripple approaches 0, the value of the capacitor is going to approach infinity, right? So basically, minimizing the output ripple is going to increase the capacitance, but increasing the switching frequency is going to decrease the size of the capacitor you need. So that's also helpful to remember. Increasing the switching frequency will decrease the size of that capacitor. And then the last thing I wanted to talk about is going to be the input capacitor, which isn't drawn on these diagrams, but these diagrams are assuming that this is a perfect source, right? So assuming your voltage source isn't ideal, you need an input capacitor. So we have our source, and we'll have an input capacitor here. And then this is our switch. So we're going to find this branch current. It's I switch This is going to be IC. It's going to be I in. So then from our switching sequence, we'll be able to see that this is time, this is IC versus time. The current in this capacitor is actually going to look like this, where this is T on, and this is T off. And then similarly, first let me mention, this is equal to minus I switch. So similarly to the output capacitor, this is going to be positive charge, this is going to be a negative charge, equal value. And the last example, these are both triangles. They're going to be the same complexity to solve, but here you can see this is a rectangle. It's going to be a lot easier to solve the area of this rectangle. So just like the output capacitor, Q is equal to Cn times delta V in. So then Q, that area, is just going to be equal to I switch times T off, which is going to be equal to C in times delta V in. So then we get C in is equal to I switch, and this is for the maximum current that we're passing to the output. So I switch is going to be equal to the maximum output current, because remember this switch is going to be passing current through this inductor, and this inductor is going to be the same as the output. Okay, so where was I switch max times 1 minus D, times T divided by delta V in, which we can further simplify to the duty. So I switch max is going to be equal to duty times I out max. Like I was saying before, when this switch is closed, the current through it is going to be the same as the current through this inductor. It's going to be the same as the current through the load. So we're doing this for the maximum output current scenario. So given that duty, the current in that switch is going to be the duty times the max output, because the switch is only experiencing it during the positive cycle of the duty. So we get D times I out max times 1 minus D, and then rewriting the period as the frequency, using the period as the inverse of the frequency, times delta V in times F. I'll write that a little better. Times F. This is going to be equal to Cn. And from that, we can see that similar to the output capacitor, if we want a smaller peak-to-peak ripple in the input, we need to use a larger capacitor. And the frequency, although not proportional to the inverse of the square, the input capacitor is proportional to the inverse of the frequency. So increasing the switching frequency is also going to help us in reducing the size of that capacitor. So overall, this video covers the basic switching properties of the buck converter, and then from that we can derive the transfer function of the buck converter, as well as the peak-to-peak current ripple of that converter. And with these relationships, we can calculate the critical inductance needed for a minimum voltage rating. So say our converter needs to be able to supply a minimum load that is drawing, say, and if we define the load as a power, so if we say P out is going to be our load, and the minimum load is some arbitrary value, right? The minimum load is going to be equal to the voltage output times the current output. And because our converter is working to convert, say, for example, this could be 12 volts to 5 volts to our load, then this V out is always going to be a constant 5 volts. So then we can say I out min is just going to be equal to this minimum power rating that we're designing for divided by the output voltage we've designed. And with that I out min, we can calculate the critical inductance needed to maintain continuous conduction mode. And a good rule of thumb would probably be to say L plus 10%, just to account for any voltage drop that is actually created across this winding due to its resistance. We could just say add 10% just to make sure that we keep it above barrier conduction, or boundary conduction, excuse me. And then we can also use these derived equations for calculating the output capacitance and the input capacitance for a desired input and output ripple. Thanks for watching.